Hello everyone. Now we are going to discuss about a topic from Antennas and Microwave Engineering subject. We will see about the introduction of microwave engineering. What is microwave frequencies? The term microwave refers to alternating current signals with frequencies between 300 MHz to 30 GHz with a corresponding electrical wavelength between 1 meter to 1 centimeter, which is nothing but the range of frequencies over 300 MHz to 300 GHz. It may be sometimes referred as 30 GHz. The range of signals between 300 MHz to 30 GHz. The range of signals are called as microwave frequencies. And a corresponding wavelength for these waves 1 meter to 1 centimeter. For 300 MHz the wavelength is 1 meter. For 30 GHz the wavelength is 1 centimeter. And we can classify the microwave in terms of three major bands called as ultra high frequencies, which is UHF, 0.3 GHz to 3 GHz. Then super high frequency SHF, which is 3 GHz to 30 GHz, and very extra high frequency HF with 30 GHz to 300 GHz. The major range of these microwave frequencies are classified as ultra high frequency, super high frequency, and extra high frequency. And this is the EM spectrum. Already we know very well EM spectrum. The spectrum consisting of various signal frequencies: ELF, which is an electron low frequency; SLF, super low frequency; and VLF, very low frequency; LF, low frequency; MF, medium frequency; HF, high frequency; UHF, high frequency; UHF, ultra high frequency; SHF, super high frequency; and AHF, ultra high frequency, infrared, light, X-rays, gamma rays, and cosmic rays. Each rays having different frequencies ranges. In this we are going to classify the microwave ranges from 3 GHz to 300 GHz, which is something sometimes it may be referred as 300 MHz to 300 GHz, or maybe generally it is given as 3 GHz to 300 GHz. Sometimes it may be referred as 300 MHz to 300 GHz. It depends. And this is the frequency band earlier, which is defined by US military, and they have classified the various bands, right? A band, B band, C band, D band, E band, F band, G band, H band, I band, J band, K band, L band, M band. The corresponding bands having the frequency ranges 0.1 to 0.25, 0.25 to 5, 0.5 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 6, 8 to 10, 10 to 20, 20 to 40, 40 to 60, and 60 to 100. These are the various ranges. A band equals to 0.1 to 0.25 GHz, and correspondingly G band belongs to 0.4 to 0.6 GHz. So this is the frequency band which is defined by US new military, and later IEEE redesigned the frequency band in a different category all over the world. And here it is classified as UHF, VHF, LHF, L band, S band, C band, X band, KU band, K band, KA band, millimeter and sub-millimeter, which ranges between 0.003 GHz to 0.3003 GHz, 0.030 to 0.3 GHz, 0.3 to 1 GHz, 1 to 2, 2 to 4, 4 to 8, and 8 to 12, 12 to 18, 18 to 27, 27 to 40, and 40 to 300, and greater than 300. And so these are all the different frequency bands which is defined by IEEE. And academic purpose and research purpose, we are going to use X band frequency signals. X band frequency range of microwave signals, which belongs to 8 GHz to 12 GHz, exactly 8.4 to 12.2 GHz. And what are the applications of microwave signals? What are the applications of microwaves? We have various applications of microwaves in the communication side, a radar side, industrial, biomedical, and heating. And if we are going to think about radar, we can use civilian services, military services, medical purposes, industrial purposes, and home applications. A lot of applications are there for a microwaves. In terms of communication, it is for terrestrial communication, and and satellite communication we can use microwaves. If we are going to think about a radar, we can think about a civilian, which is mainly for air traffic. Right, air traffic control, air traffic navigation, ship safety, space vehicles, remote sensing, law enforcement. We have the various applications in a radar. And if we are going to think about military, the military radar service in the military, as well as surveillance, navigation, guidance of weapons, and electronic warfare, CQ. These are the applications includes the microwave. And if you are going to think about industrial or biomedical, and we can use the microwaves for following the applications of process control, drying, curing, treatment of elastomatoes, waste management, nuclear elastic monitoring, imaging, hypothermia. And if you are going to think about heating, microwave ovens are available, no? So we know about the microwave application of microwave oven, which is mainly used in household applications. For industrial purpose, we can use microwaves to heat the elements. What are the advantages of microwaves? Right, it can carry large quantities of information because of high operating frequency, and have the high frequency is very high, automatically the low wavelength having, and it requires very small antenna to transmit the signals. Automatically frequency increases means we know about that wavelength gets decreases. The wavelength get decreases means automatically size of the antenna to transmit the signal from place in the place. It's also very small, and the microwave signals are easily propagated through space. And fewer applications, few repeaters are necessary for amplification in terms of satellite communication. And here we have increased bandwidth because of the signals are operated in gigahertz frequency range, so we have a increased bandwidth. And what are the disadvantages? Even though we have more advantage, we have some amount of disadvantages also. And these microwaves are difficult to analyze and design. The microwave components or microsystems are analyzed. It's very difficult to analyze and also design. And measuring techniques are more difficult. The measuring techniques available in this microwave communication is very difficult, and difficult to implement conventional components such as microwave frequencies. It's difficult to implement conventional components like resistor, capacitor, inductors are very difficult to design in microwave frequency range. In low frequency range, you can easily design the following components, but in terms of high frequencies, so it's very difficult. And transit time is more critical at microwave frequencies. Transit time is nothing but around the time. The time taken by the anode, the time taken by the atom to reach from anode to cathode. It's also very high in terms of microwaves. It's very critical value in microwave communication. And we will think about next we will see about the basics of antennas. Previously we discussed about some basics of microwave. Now we are going to discuss about the basics of antennas. And what we are going to discuss about this antennas nothing but introduction to antenna, characteristics, and also types. Elaborately we will see some in terms of brief introduction about antenna introduction. So antenna is an electrical conductor or system of conductors to transmit or receive the electromagnetic signals. So transmission, it radiates electromagnetic energy to free space, and reception, it collects electromagnetic energy from the free space. The diagram itself you can able to understand. Left side we have a transmitting antenna, right side we have a receiving antenna. Transmitting antenna is connected with a transmitter or something but a generator. It's going to generate the microwave signal or electrical signals which will be transmitted, and it is connected to coaxial cable or transmission line cables, and at the end we are going to connect our antennas. During the transmission of with signals in a transmission line, it will be guided. Once it reaches the antenna, it's converted into guided waves in terms of unguided waves. It's nothing but free space waves. At the receiving side, it's going to receive the unguided wave signals, and it converts the guided unguided into guided waves, and it will be given to receiver. What are the role of antennas? Right, the antennas they serve for four primary functions. The four important functions of antenna: it will act as a spatial filter, it will act as a polarization filter, it will act as an impedance transformer, and also it will act as a propagation mode adapter. A spatial filter is nothing but directionally dependent sensitivity. So the antenna is mainly depends on direction. It's going to receive the signals in a particular direction. It is very important spatial filter. Even though it's going to be in a space we have a lot of signals, the corresponding antenna is going to receive the corresponding signals from the corresponding direction by designed by the manufacturer. The second one is polarization filter. It is polarization dependent sensitivity. The signals are transmitted in a particular polarization, means the receiver is also going to receive the particular polarization signals only. Impedance transformer, a transition between a free space and a transmission line. The free space having a different impedance value and transmission line having a different impedance value. That impedance values are transferred by antennas. And propagation mode adapter, free from space fields to guided waves. And propagation mode is nothing but it's going to free fields, free space fields to guided waves. Right? In a transmission line, the waves are available as a guided signals, guided waves, and a free space is going to change as a unguided waves through transmission line and also wave. And spatial filter, antennas have the property of being more sensitive in one direction than in another, which provides the ability to spatially filter the signals from its environment. From the diagram itself, you can able to understand the directive antenna, and also it's having some radiation pattern in a particular direction. Polarization filter, antennas have a property of being more sensitive to the one polarization than another, which provides the ability to filter signals based on its polarization. Simply we can say it, if the transmitting antenna is going to transmit the signals and the transmitting antenna is vertically polarized, means the receiver antenna also we have to have a vertically polarized receiving antenna, then only it will be able to receive the vertically polarized transmitting signals. An impedance transformer, we know that coaxial cable or transmission line having different impedance value and free space having different impedance value. That impedance value will be managed by antennas. The entrance impedance of a free space will be 377 and the impedance value of a transmission line or coaxial cable is 50 ohms. So this impedance mismatch value will be managed by antennas. And propagation mode adapter, during the both transmission and receiver operations, the antenna must provide the transition between the two propagation modes. From the diagram itself we can able to see. And antenna types, we have different types of antennas. We have end fire, we have loops, we have dipoles, we have stubs, we have slot, we have aperture. And end fires we have polyrod, helices, Yahoo, long periodics, conical. And dipoles we have holder dipole, array antenna, curtains, WHJKS, and holder dipole we have twin lines. Then we can classify into V's, biconical, long waves, beverage, or rhombic. And slats we have a patch antennas, arrays antennas. And aperture is a very big area. We have a lenses, spirals, horns, or reflectors. Again, reflectors will be classified into flat, corner, parabolic, randoms. And these are some diagrams of antennas. So this one is the helical antenna. This one is helical antenna, and this one is horn antenna, this one is parabolic reflector antenna. And characterization of antenna. What are the characteristics of antenna? These are all some small number of characters are available in this slide. And directivity, power per turn, antenna gain, and antenna efficiency. And this is the radiation pattern. Variation of the field intensity of an antenna as an angular function with respect to the axis. And this is the radiation pattern. This radiation pattern consisting of a major lobe, right, main lobe or major lobe, and this is the back lobe, side lobes, and zero null lobes. This is the Agid antenna. This antenna having three components, right? Minimum three components. One is director, driven element, or reflector. In detail, we will see in later classes. And this is the 3-element antenna radiation pattern. And this is the practical antenna 2.4 GHz Yagi with a 15 decibel gain. And this one is the log periodic antenna, which consisting of a lot of dipoles. It can be able to expand and contracted. And this is the parabolic reflector, and different type of antenna, parabolic reflector. It's also called as a dish antenna. And this is the example for Stanford big dish. And this is a patch antenna, right? And the size of the patch will be rectangle, square, triangle, circle, semicircle, whatever may be. And this is the array antennas. A similar type of antennas are arranged to get to increase the antenna characteristics. So here you can see that A and B is one set of antennas. Two antennas are connected together, and we can able to connect these four antennas in a single line. And this is the patch antenna for spacecraft also we are going to use the patch antennas. And very large array, you can able to see a similar type of antennas are arranged in a line to increase the antenna characteristics. And this is also an example for antenna arrays. Different types of antennas are arranged. And this is the satellite TV antennas. You can see these type of arrangements in a what you can say, these type of antennas are available in cities. Like we have some flags, and this is Owens Valley Radio Observation Observatory array, and this is New Mexico Large Array, and this is 2 GHz adaptive array antenna. It can be able to receive the signals in a particular direction. So the remaining we will see in another class. Thank you.